Hello guys, this is my second video on differential equations. In the first video we covered linear differential equations, and I was thinking I would be able to cover Bernoulli, but I was not able to do that because I didn't want it to be too lengthy. But I have a summary of what I have from my first video, and if you want more details on linear differential equations, you can check it out. It is labeled Differential Equation Lecture 1. So this will be Differential Equation Lecture 2. And to recap, we have the general form for linear differential equations as this: dy dx plus p of x y equal to q of x, where x is your independent variable, y is your dependent. To solve this kind of equation, you have to find something called the integrating factor. The integrating factor mu is equal to, rho is equal to e to the power of integral p of x dx. Now, having found the integrating factor, multiply your general form with the integrating factor. Your left-hand side reduces to this, and your right-hand side stays at this. To find the solution of this, you just integrate both sides. This goes away, and you have integral this plus c, and then you divide all through by rho, which is the integrating factor. Yeah, you should check out the first video. You will see the step-by-step how I used it to solve a question. Now we'll cover contents in Bernoulli differential equations, and we'll see how we solve a question of that nature. So the general form for Bernoulli differential equation is the y dx plus p of x y is equal to q of x y n. The difference is that Bernoulli has this extra term, whereas linear does not have it. Now, the key to solving this equation is to use a substitution v is equal to y to the power of 1 minus n. This helps you reduce your Bernoulli to linear. It helps you reduce Bernoulli to linear. And when you have it in this form, you can use the same procedure to integrate or to find a solution, after which you will replace your v back with y1 to the exponent 1 minus n. So let's just substitute this in here and see how it works out. So first of all, we want to find dy dx in terms of v. So we will differentiate this substitution. Here we have 1 minus n, y 1 minus n minus 1, because the exponent comes down, you reduce it by 1, right? And then you have dy dx here, because we are differentiating y on this side, on the right hand side, with respect to x. Rewriting this, we have the v dx is equal to 1 minus n. This we cancel this, so we have y to the exponent minus n dy dx. Now I can make this guy subject, and I'll have dy dx is 1 over 1 minus n y to the n dv dx. Now, I divided both sides by 1 minus n, and I multiplied both sides by y to the n. And that's how I got this. Now we're going to substitute this back in here. Anywhere you see dy dx, you're going to have this. So dy dx is this. So we have 1 minus n, yn dv dx, right? And then you have plus p of x, right? Y. And then you have equal to q of x, yn, right? Now, I can divide all through by what? Y to the n. I divide this side by y to the n, divide this by y to the n, divide this by y to the n, right? When you do that, you end up with 1 over 1 minus n dv dx plus p of x. By indices, this is y to the 1 minus n, right? And this last part becomes q of x. Remember, y to the 1 minus n is v. So by updating, we can multiply all through by 1 minus n if you want to. So we have dv dx plus 1 minus n p of x. This becomes v is equal to 1 minus n q of x. Now, your new p of x is all this together. P of x. And your new q of x is all this together. But if you look at it, it is exactly linear with dependent variable v, and your independent variable is still x. Now you can use this approach to solve it. This is a weird representation in my own opinion, and all the textbooks I've seen have your Bernoulli expressed as this. I like to express my Bernoulli in a different way. It makes it easier to simplify. My expression, and I'm going to use a different exponent so we don't get confused. My general form, or the way I like to have it, is yn minus 1, or let me use m, so it's different, n minus 1 dy dx plus p of x ym is equal to q of x. Now, this is the way I write Bernoulli, general form, it's convenient for me, and you'll see this in a short while. So any equation that can be, differential equation that can be written as this is Bernoulli differential equation. For convenience, I write it this way. Any differential equation that can be written in this form is Bernoulli differential equation. This can be written in this form, and is preferred this way. If you write it this way, your substitution v is simply y to the n. When you use this substitution, it reduces it to what? Linear. And let's try that. So dv dx is equal to what? N minus 1 dy dx. Now, I just need to divide both sides by n. Right? This goes away. What do you notice? Okay, I'm using m. So not n, m, m, and m here. M. So what do you notice? Y to the m minus 1 dy dx, I have it here. I will just replace all this with this because they are equal. So now I would have 1 over m dv dx plus p of x. Instead of y to the m, I have my v is equal to q of x. Transforming it is so short, 2 steps compared to this. And it's linear. All I need to do is multiply all through by n dv dx plus mp of x, v is equal to mq of x. This is my new p of x, and this is my new q of x. So this makes it easier, and it is exactly linear. Now you can use this approach to solve it. I'm going to use this to solve the question real fast. I prefer this method. So I have a simple question. I'll just continue here. I don't like this one. Is it? Okay. I'm going to solve an example using this form. Most likely, it's going to be given in the form we had here, because all the textbooks I've seen have it in that form. So I have an example, x dy dx plus 6y equal to 3xy to the 4 over 3. See? Like I said, is given in the form I had here. I want it to be in this form. If you notice, q of x has no y here, right? So to write it in that form, you just divide all through by this. This becomes x y minus 4 over 3 dy dx plus 6. This becomes y 1 minus 4 over 3, right? Indices is equal to 3x. One other thing you can do is divide all through by x, right? Right? This becomes y minus 4 over 3 dy dx, right? This gives me plus 6 over x y. This is the same thing as 3 over 3. 3 minus this will give me minus 1 over 3, right? And then equal to 3. So I have successfully written it in this form. Y to the n is what is multiplying my p of x. My p of x is 6 over x, right? It implies that to convert or to reduce it to linear, I have to use the substitution. V is equal to what? Y minus 1 over 3. Let's see how successful that will be. So let's differentiate this. We have dv dx is equal to the exponent comes down and we reduce it by 1. This becomes minus 1 over 3 y minus 4 over 3 dy dx. What you just need to do here is to multiply both sides with minus 3. So we have minus 3 dv dx is equal to y minus 4 over 3 dy dx. Look at this right hand side and look at this. Can you see? Identical. So you just replace this with this. So we have minus 3, therefore minus 3 dv dx plus 6 over x. This is what? My v. Remember? V is equal to 3. Now I need to multiply all through by divide all through by minus 3. And then it will give me dv dx minus 6 over 3, which is 2 over x v equal to what? Minus 1. Simple and clear. Now you have your new p. This is my new p. And this is my new q. And that's what we'll use to solve this question. And I'm going to continue there. Let me just finish it up because it seems simple enough to pull up. So I'll wipe the side and finish it up here. So example continuation. So we have dv dx minus 2 over x v equal to minus 1. So our linear differential equation is in x, but the dependent variable is v. So now we find the integrating factor is what? E integral p of x. Let me write my integration well. Dx. And this will give me E integral minus 2 over x dx, which will be E minus 2 ln x. And this exponent can come up here to give me E ln x minus 2, right? This will cancel this, which will give me x minus 2. This is my integrating factor there. So remember, d dx of integrating factor dependent variable is equal to q of x integrating factor. That's what we need. So d dx integrating factor dependent variable in this case is v, right? Equal to q integrating factor. Can you see that? Integrate both sides. This is what you have. So I could have just used this last expression, but the result, the left-hand side will be v. So we have v here is equal to 1 over integrating factor into integral minus x minus 2, because that's what this will give me, dx plus what? C. Integrate this one. 1 over x minus 2 is x to the 2. So we have x squared. This will be minus x minus 2 plus 1, which will give me minus 1, right? So I can just say minus 1 divided by the new exponent plus c. This will give me v is equal to x squared 1 over x, because 1 minus minus will give me positive, but x to the negative 1 is 1 over x plus c. Now, we've solved the linear equation, but our dependent variable is not v. Recall, dependent variable is this. So we have to update it. Recall, v is equal to y minus 1 over 3. So we have to put it back here, right?
Right.
So we have y minus 1 over 3 is equal to what? X squared 1 over x plus c, right? And then it just means we can open this bracket if we want. Just raise both sides to -3. This will cancel all this, and we have y is equal to x 2 1 over x plus c -3. We can rewrite this in a better form. This is, because it's negative, you can write it in this form. X squared into 1 over x plus c all to the third. Now, because it's negative, everything can go down, and you can expand the 1 inside, right? So really, I could have, I could have expanded this, and I will have x here plus c x squared, right? I can try and squeeze it in, but basically that's the solution. So we start with Bernoulli. I reduce it to the form I like. I figure out what my y to the m is, replace it with v, transformed it to linear, use the same approach we have in linear to solve it, and then update my solution by replacing that fictitious variable with the original variable, or the variable I used with the original variable, and simplify further. And that's how you basically solve Bernoulli differential equation. Essentially reduce it to linear. This marks the end of this video. I would have another video, and I will discuss Bernoulli-like differential equation. They are differential equations that looks like, they all look like Bernoulli equations, but they are not Bernoulli. They are similar in the sense that you can use the same approach that you use in solving Bernoulli differential equations. Thank you very much.